Hello, everyone. Let's see here. Welcome to our first in a series of learning webinars for our industrial customers, with today's topic being generator protection and applications, with a short introduction on programming one of GE's newer protection relays, the 889, a member of the 8 series family. I'm your host, Tim.
I don't know who your family is.
Oops. As your host, my name is Tim Fahey, Regional Sales Manager out of Raleigh, North Carolina, and I'm also joined by Eduardo Iglesias out of Florida. For our presenter today, we have Mike Romlachin, who's a GE Technical Application Engineer based in Florida, and we also have Technical Application Engineers Christine Kreitz in Ohio and Terry Smith from Tennessee to support any questions that you may have as we go. The attendees for this webinar will be muted, and we ask that any questions you have, you put in the chat box or the Q&A box, and we'll answer these as we go, or we will address them at the end of the presentation. We will be recording this session, which will be available to you for the next 60 days through the same calendar link that you used to join this meeting. And training hour certificates for the session will be sent within 2 weeks for this presentation to those who have attended. It's important that if you joined by phone or anonymously, to send your name by email or in the chat box, so that we make sure that we send these certificates to you. With no further ado, I'll hand the session over to Mike for the session on generator protection. Thank you.
Thank you, Tim, and welcome everyone to today's presentation on generator protection. Just some housekeeping items. As Tim mentioned, the webinar will be recorded and will be available for about 60 days through the same attendee access link that you've used. So at the end of the presentation, if you want to review the recording, you just access the same link and you can play that recording. For the certificates that Tim mentioned, please follow his instructions if you need the certificates. And please, all the attendees will be muted. If you need to ask a question, please put the question in the live event Q&A box, and we will answer them to the best of our abilities. So with that, let's get started with today's topic. And the first thing we want to tackle when we talk about generation protection is how is the generator grounded and what type of connections, how it's connected to the system, because this will determine what type of protection we need to apply to our generator protection system. So when we talk about generators, generators that we know are can be very expensive and important, and they're important parts of our process. So we want to maximize the uptime to the process and maintain the revenue generated by having the generator maximizes its uptime. Repairs or replacements of a generator can be very costly, notwithstanding the loss to the process and loss to the revenue during the downtime. So we want to reduce or limit exposure to downtime of the generator. And one of the things to be able to do that is to reduce the effect it can see for short circuits. And we'll talk about some various type of techniques, grounding techniques that we use to be able to do that. If the short circuit fault current is limited or less than 10 amps, there will still be damage in the generator, specifically damage to the metal in the generator laminations. So we still need to detect, even if we are going to eliminate the fault current, we still need to detect when there's a fault in the generator. The grounding strategy employed is a key factor in determining the magnitude of fault current, and we'll talk about some of those grounding strategies. There are several grounding schemes and strategies commonly used to protect the generator. These grounding schemes will be reviewed based on the magnitude of fault current, ease of detection, and the reaction time of the protection elements to minimize damage. Grounding provides for us a safety, number one, safety by allowing detection of fault within the equipment. So if there's a ground fault, there's a path for ground current to flow. So our relays can detect that ground fault current and be able to isolate that faulted piece of equipment. Also, if it allows us to stop transient overvoltages or reduce transient overvoltages. For ungrounded systems, if we recall, when we have a fault in an ungrounded system, the neutral shifts. When the neutral shifts, the grounded phase shifts to the neutral point, and then the ungrounded phases shift to the phase-to-phase voltages. So we have very high transient overvoltages that can damage the equipment, damage installation, break down installation. Ability to detect the ground fault to detect ground fault before it evolves into a multi-phase fault is very important, because as we know, multi-phase faults can cause large amounts of fault current to flow in the protective equipment and not only cause permanent damage to that equipment, but maybe collateral damage to the surrounding equipment. The strategy to limit ground fault current and hence potential for damage is the proper grounding, whether it's true on impedance, whether it's a low impedance or high impedance, and we'll talk about both of those types of grounding that are common. This is a basic example of a generator connected to our power system. In this case, we're grounding it through a low impedance resistor. It provides a ground source for the system so that if there is a fault current, phase to ground fault in the system, ground fault flows up into the neutral of the generator through that resistor and completes the ground path. Depending on the fault current level, it can be very expensive to install such a resistor, because if the ground fault is in a couple of hundreds of amps, we're talking I squared T rating, I squared R rating goes up. So we need to have a higher rated resistance to be able to handle that. So it can be very expensive to be able to do that. Also, because the generator is now susceptible to high levels of ground fault current, it can cause permanent damage to the generator. So it's basically between having to replace the generator or minimizing the damage so the repairs can be done on site, minimize the outage time, and minimize the downtime of the generator. The other type of grounding that we're going to talk about is the high impedance ground. What it is there's a grounding CT in the generator ground path, which provides a high impedance to ground. What that allows us to do, it uses the principle of reflected impedance, where we'll be able to reflect the primary impedance over to the secondary and hence have a high impedance to ground. And the formula to do that, put that up there, it's the resistance reflected is going to be equal to the resistance that it's in the ground circuit there, the RP resistance times the turn ratio of that transformer. Why we do this, obviously, is to limit the ground fault that the generator is subjected to when there is a ground fault to very little or practically no ground fault being seen by the generator. This allows the generator to be able to operate without any damage, but if that ground fault current is allowed to linger on for a long time, it can cause fault situations in the generator, such as as I mentioned, damage into the metal over time, and cause some minimal damage, which can lead to from evolving from phase-to-ground fault to phase-to-phase fault and catastrophic damage. So we need to detect, even though it's very limited ground, we need to detect those ground faults. And it's very difficult to do it, because how can we detect the ground fault when we can't see any ground current? But there are techniques that we will use that we'll talk about to be able to do that. Ground fault typically, in this case, would be very low, as I mentioned. We're talking about less than 10 amps of primary current. Also, some of these installations will have a GSU connected to it, so that transformer generator step-up transformer connected to the ground to the system through the generator. And we do this to isolate ourselves from the system ground. So if we have a delta to Y transformer, which is most of the GSU's case is a delta to Y, so if the delta is on the generator side, it allows the generator to be isolated, to be ungrounded, while on the system side, it's a Y grounded winding, so it allows the system to have its ground so that if there's a ground fault on the system can detect that ground fault and be able to take corrective action. Or at the same time, if there's a ground fault on the generator, we don't see any ground current in the generator. The other type is a little more complicated grounding scheme, which is we refer to as a hybrid ground. Obviously, as the name suggests, it's a combination of a high impedance ground and a low impedance ground. So normally, the generator is operating where this VS, the vacuum switch is closed, so the generator is normally grounded through a low impedance resistor. When there is a ground fault, the ground detector, like the 87, the ground differential, will trip quickly. It will open the generator breaker, open the vacuum switch to limit the ground fault current. So now it goes from a low impedance ground to a high impedance ground. So it limits the damage caused by the ground fault by turning it into a high impedance ground, and then it can open the generator breaker. So basically what the system is doing is converting a low impedance grounding circuit to a high impedance ground for an internal generator fault. The caveats to this is we have to have a protection that's very fast. It's got to detect that ground fault very fast because we don't want it to linger on for a very long time. And the vacuum switch has to be very fast acting. So that vacuum switch needs to be quickly be able to open up that low impedance path to ground and enable the high impedance path. How do we connect the generators to our system? One of the most basic is the direct connected or bus connected system. This example is showing two generators connected to our bus and to each other through that bus. This is typically seen in industrial, commercial, and isolated systems, not so much in the utility side or larger generators. It's simple, inexpensive. The disadvantages of using the system is the generator is likely to be permanently damaged for an internal fault current. Because again, it's a low impedance ground, so if we have an internal fault in the generator, we'll see high ground fault currents and it's susceptible to being permanently damaged. And the other problem we have, especially if we have two generators connected to the same bus, is to discriminate which generator that ground fault is on. So if the generator on the left has a ground fault, both generators will see ground fault current because they're both grounded through low impedance ground. The other configuration is sharing through a GSU or a step-up transformer. This is more likely in larger industrial systems where the system might need to be connected to utility. In this case, the utility requires the isolation, where for a fault on their system, they have their ground fault current, and where it's a fault in the generator, ground fault in the generator is isolated from the system ground. However, the same issues, disadvantages here is how do we discriminate which one of these generators the ground fault is on. What we're going to talk about today, a lot of what we're going to talk about today is going to be focused on this connection, which is the unit connection. And you'll find this a lot mostly on large utility or industrial systems, and it's transformer between the generator and the system, and the generator is high impedance grounded. Typically, you might have an auxiliary transformer, and that auxiliary transformer is usually there to provide some light and power load, some auxiliary load when the generator is running or when the generator is offline, where it can be backfed from the system. Both the GSU and the auxiliary transformer is delta grounded on the generator bus connection. So again, to isolate the grounding from the system and from our loads from affecting the grounding in the generator. So if there's a fault out in the system, fault out in the load section, the generator does not see that ground fault, only for faults within its zone. So the reason we do this, as I mentioned, this is usually large industrial utility systems. So these are fairly larger generators, so much more expensive, more important to our process, generating revenue for customers, driving a large process. So we want to limit the damage that's going to be caused by ground faults. And as we know, most fault situations that happen in our power system, the majority of ground types that happen in our power system are face to ground faults. And again, as I mentioned, the GSU and the auxiliary transformers are connected in delta to be able to isolate the generator ungrounded system from the grounded and the load side grounded systems. Let's talk about how the generator is operating. So when a generator is connected to the system, it's connected maybe through multiple lines, whether it's transmission line, distribution lines, whether it's in a utility feed or an industrial feed. You might have multiple lines connecting to your generator, multiple switchgear sections connecting to that generator, multiple loads off of that generator. And there's always a delicate balance between those loads and our generation. Our system will contain multiple load pockets, multiple generation, and there's a constant balance or delicate balance that must be maintained between the generator output and the load requirements. So in order to maintain this balance and control that balance, there are controls that are associated with the generator, specifically voltage and frequency controls, usually referred to as the excitation control system or the VAR controls voltage control system. When our generator is operating for best efficiency, it should be operating near or close to the full load rating. So usually, if a generator is called upon to operate or be in service, we want to be operating as close to full load for efficiency purposes. There are generators that might, when they're called upon to operate, that are not necessarily going to be operating under full load because of the requirements of our loading. If our load doesn't require the full load rating, then obviously we need to derate the equipment and run it at the load levels. When we talk about the generator, like any piece of equipment, there's a limit as to how we can operate the machine. Usually, as the stator limit is what we're going to be mostly operating in, and that's where we're generating real power into the system, with usually in a generator with some lagging power, with some leading power factor, so that we can supply VARs into the system to be able to maintain the voltage stability of the system. And this generator capability curve, it defines the boundary within which it can deliver real and reactive power continuously without causing overheating in the generator or damage in the generator. So what we really need to be operating is in this red part of the curve for the normal operation of the generator. Once we start to getting outside the red part of the curve, we go in the blue, the overexcited portion of the curve, which we refer to as the OEL, or the overexcitation limit of the generator, or the underexcited part of the curve, which we usually refer to as the MEL, or the minimum excitation limit of the generator or machine. When we're in the underexcited part of the curve, the machine becomes inductive. It becomes like an inductive motor, so that it starts to draw high reactive current, which overloads the stator, induces currents in the rotor, and causing overheating in the machine and over time damage to the machine. Overexcited conditions that can occur are if we lose the field. If we lose the field control, we lose our control on the field, we can be in that underexcited limit. And there is certain protection that we call loss of field protection that we'll talk about to be able to deal with those conditions. When we are in the overexcited part of the curve, situation that can cause us to go into that overexcitation limit of the generator is again control failure. We're not be able to control the generator properly and it's starting to get overexcited. Operational error during offline manual regulation operation. Loss of the sensing voltage to our automatic voltage regulator. So the system is not reading the correct voltage, so it might be going to an overexcited condition because it thinks it needs to supply more VARs. System problems such as load rejection or islanding. So when we certainly lose loading, the machine cannot correct instantaneously, so it goes into an overspeed condition and then into an overexcited condition. The overexcited condition not only affects generator, but it affects transformers too, because the transformer, as with the generator, the core windings become saturated and that causes overheating. Flux start to flow where they're not meant to flow and causes overheating and damage eventually. So just a holistic view of the connections of generators or loads and our transmission lines, distribution lines, how they interact with each other. Generators might be within closer load pockets, or they could be far away from our load pockets, like hydro generations. Those are located far away, so we need to have high voltage transmission lines going out to remote locations to be able to transfer that power to where our load pockets are located. Then we might have in-city generation. And all the time, there's always a delicate balance between our generators and our load. And the generators balancing against each other. So if one generator starts to misbehave, all the generators will start to follow suit and start to misbehave, and we have to detect those conditions and be able to stabilize for those conditions. Let's talk about when we look at generator protection, what specifically do we need to do and how do we protect it? As with any type of protection, when we look at protection in general, there's always a delicate balance between certain design consideration when we're talking about protection. We want the system, the protection system, to be reliable. We want it to be highly reliable, where we need it to trip when there is a fault on the system, and we need it to trip in a specific amount of time. So when we talk about reliability, there's a delicate balance between dependability versus security there, where we want it to trip for faults, and obviously we don't want it to trip for non-fault situations. And then how effective that protection system is, how fast does it trip for faults within its zone of protection, or how fast it trips for faults outside of its zone of protection. How does it coordinate for faults outside of its zone of protection, and selectivity to only trip for faults within its zone of protection, unless for faults outside of its zone of protection, the protection elements that are associated with those systems are not operating properly. Then we want to trip the generator, protect the generator from outside faults, outside zone faults. So consideration for settings. We'll talk about a lot of those considerations, but there are relevant IEEE guides and CIC guides that we can look at. There's working group committees within IEEE that came out with these guides, and we can look at the recommendations. We'll look at some of these guides at the end of this presentation. The generator manufacturer's recommendations, obviously the machine capability curve that is determined by the generator manufacturer, so we need to be operating within those curves. Coordination with generator controls and other control systems within the generation, and outside of the generator, the system protection functions, we need to coordinate with stuff outside the zone of the generator. So it's all a delicate balance, and also experience as a protection engineer. What is your experience designing these protection systems, not just your own experience, but experience from, historical experience. If it hasn't, the age-old thing is, if it hasn't been misoperating based on a certain design, why mess with it? So what are we protecting against? We're protecting, obviously, for internal faults within the generator, short circuits within the generator, and we're protecting against internal abnormal operating conditions, as well as we need to protect for faults outside the generator zone or faults in our, we refer to as system faults. So the task of the generator protection is to avoid problems from internal short circuit, these abnormal operating conditions that we'll talk about, and from the system faults. These abnormal conditions are not just short circuits. So when we talk about abnormal conditions, these are for internal abnormal condition. These are overexcitation, abnormal frequency operation, reverse power, breaker failure, inadvertent energization of the generator, a breaker pole flashover, and some of the external non-short circuit conditions can be loss of sync during a power system disturbance, open phase out in our power system, and so we need to protect our generator from all of these conditions. So let's focus first initially on how do we protect for phase faults within the stator. So within the stators, there's different types of fault. There can be interturn faults between the various coils within the generator, and then we can have coil-to-coil faults within the same winding of the generator. Then we can have face-to-face faults between the various windings of the generator. The commonality within all these faults is we're not going to see ground fault current. We're not going to see zero sequence elements, so any type of ground fault, zero sequence protection. Chances are we might not be able to pick those up. So we need to be able to protect against these phase faults and be able to coordinate for phase faults outside the generator zone within our system, and within our power system. So phase faults are not limited by the type of grounding we discuss, right? Because phase faults don't involve ground, so the grounding resistor, whether it's low impedance or high impedance, does not come into the picture. The GSU does not provide isolation for phase faults, so we will see phase faults within our power system reflected into the generators, into the generator. Current requires coordination for system faults and will be slow. Damage can be catastrophic if the fault currents are high and are not removed immediately. So whatever protection we have for faults within, phase faults within the generator zone, we need to be able to isolate quickly. And the type of protection to be able to do that we use is the differential protection, or 87S. I don't know if everybody's familiar, but the differential principle is basically looking at currents entering the generator and currents leaving the generator. Under normal conditions, loading conditions, or external fault conditions, current entering the generator and entering the neutral of the generator, neutral CTs of the generator, and leaving the terminal CTs of the generator are equal. So when we say differential, we're doing a subtraction between those two currents and vectorial subtraction. So for faults outside the zone of the generator, the current in should be equal to the current out. So we have a zero differential current and we will not operate. For faults within the generator zone, the currents are entering, again, the neutral CTs of the transformer and entering the terminal CTs of the transformer. So now they add vectorially and you will see a high differential current, and we will use that principle to trip the generator immediately for phase faults within the generator zone. The beauty of this type of protection is we don't need coordination. We don't need to coordinate for external faults. It is inherently secure against external faults. It is high speed. We're talking about cycle to a couple of cycles, depending on the type of relay. The main issue with this type of protection, as with most type of protection, is CT saturation. So we need to size our CTs properly, and we'll talk a little bit more about CT sizing and how CT saturation affects our protection. The CT selection and burden makes a big difference when we talk about CT saturation. When we size our CTs, we need to size our CTs to as much the best of our ability to avoid saturation. So we need to size the CTs for maximum fault current level. We need to minimize the burden seen by the CTs, as CTs are rated for certain excitation voltage across their winding. If we exceed those excitation voltage, we will push the CT into saturation. So the higher the burden on the CT, the quicker we will push that CT into saturation, because the larger excitation voltage it will see across its terminal. So what is CT saturation? What's the phenomenon of CT saturation? What does the relay see? Basically, the relay sees currents that are not reflective of the primary currents flowing in the system. So in our generator example, if we have a saturation in the terminal CT, we're not going to see the primary currents that are flowing in that system. So we might have a difference between the generator neutral and generator terminal CTs, and that can cause the generator differential to trip erroneously. With microprocessor relays, burden so much is not a concern anymore, because microprocessor relays are very low burden to CTs. Electromechanical relays had large burdens. Most of the burdens when you talk about microprocessor relays will be in the CT wiring from the generator relay out to that CT. So that's a very long distance, you want to be able to have large gauge CT wires, like 8 to 10 gauge CT connections, so you can reduce the burden. What we cannot avoid is, if our system is a high X over R ratio, we cannot avoid pushing the CT into saturation region quicker. So the things that we can control is the burden and the CT sizing. So the C37.110 recommendations for CT sizing, about 120 to 150% of the generator rating. Use the full winding ratio, meaning if you have a multi-tap CT, try to use the full winding, because if you use one of the tap windings, that will reduce the rating of the CT by the amount of that tap. So if you use, like, for example, if you have a 2005 CT and you use the 1005 tap, you're effectively reducing the rating of the CT by as much as half of what it's capable of. And you want to use CTs with the largest practical secondary voltage capability, meaning the excitation voltage want to be as high as possible. So when we rate CTs for the IEEE rating is usually C800, C400, C200, and the numbers behind the C is basically the secondary voltage capability. So C800 will be able to handle as much as up to 800 volts across the CT terminal and be able to reliably convert the primary current to secondary current. This last point here with differential CTs on both sides of the generator should be the same ratio. Yes, but not so much true anymore when we talk about microprocessor relays, because microprocessor relays can handle differences between CT ratios and connected burdens and CT ratings, but to get the maximum operation out of the CT, you want to be able to, as much as possible, to keep these within the same ratio, rating, connected burden if you can. If not, then you have to adjust certain settings within the microprocessor relay to deal with these deficiencies. So modern microprocessor relays can help when you have these deficiencies. And one of the ways we do that is we use the dual slope breakpoint curve, where Basically, there's a slope 1 and a slope 2. When we're operating in the slope 1 region, that's where we're normally operating. We're operating during normal loading conditions or within high resistive grounding faults within the zone of protection. So we expect our CT to not be susceptible to saturation within this region. So our slope can be set lower between our differential and our restraint. Now, when we're talking about maybe like internal faults or close-in external faults where the CTs are then subjected to high fault currents, where it's more susceptible to having large differential ratio errors because one CT might saturate and the other CT has not saturated. On the relay, we'll see that as a fault current. What we do is we raise the slope setting for those scenarios so that we need a higher level of differential so we can deal with certain level of CT saturation and be able to still reliably detect for internal faults and restrain from tripping from external faults. The other principle that we have applied is a directional principle. Obviously, again, current in should be current out vectorially. So faults coming into the generator and leaving for external faults coming in and leaving. The difference between those, the angular difference between those faults should be greater than 90 degrees, or technically it should be 180 degrees. Or when there's an internal fault, there will be less than 90 degrees or they're within basically 0 degrees of each other. Now, you'll notice that's kind of contradictory what I said with the angles that I'm showing at the bottom, where for an external fault, I'm showing 0 and 0, and an external fault, I'm showing 0 and 180. But that's because of how we connect the CTs in our generator relay. So it will depend how we connect our CTs. In this case, I'm showing the CTs on the generator neutral side are connected towards the generator neutral terminals, whereas the CT on the terminal sides is connected away from the generator terminals. So that's what introduces that 180 degrees. So generator connection for differential connection of the CTs are very important to get that right. This is a typical connection of the 8898 series generator differential relay. And you could see the CTs on the generator neutral terminals. The polarity of those CTs are connected to the polarity side of the relays, whereas in the terminal side of the the generator, it's the opposite. And that's where that 180 degrees comes in. And the reason we have to do that because for metering purposes, because we need to measure the flow of power into the power system. So be able to measure positive watts into the power system. So we need to connect the CTs in this configuration to be able to measure the right flow of power, but it causes an issue with our differential, so we need to correct for that 180 degree shift. This is the 889 connected if you have an in-zone transformer. And then you can see, because if you have an in-zone transformer, now you're connected to maybe the CTs and the transformer bushing, so you have to be careful with that connection, make sure it's properly connected if you're using a differential protection, so that when for internal faults it adds, and for external faults it subtracts. The main points to remember for differential is to avoid saturation, size the CT properly, but if unavoidable, then match the CT characteristics and burdens as best you can and take care of it in the relay settings. G does use a patented algorithm to defeat CT saturation or take care of CT saturation, which is we detect CT saturation, and if we do detect the CT saturation, we use the directional principle to also say, hey, is the fault within the zone or not? If it's not within the zone, then we won't trip. If it's within the zone, then we trip. so that we'll be able to deal with CT saturation issues. So inter-turn faults or coil-to-coil faults will not be seen by the differential element, and we'll see in the next slide why that is. So we need to be able to detect those faults by various means, and one of the means is what we call the unbalanced current, or maybe a negative sequence current or negative sequence voltage element. So this is an example of a coil-to-coil fault, in the same winding. And this is applied when a generator is wound with two three-phase windings, each brought out separately out of the machine and connected in parallel. With this case, if the fault is within the coil-to-coil, the current will circulate within the windings and will not be seen at the terminals, either at the neutral or the terminal side. So one of the ways we'll be able to detect that is using a split phase protection, or one CT, and that CT is installed similar to a core balance CT, where the circular currents are added when we have those circulating currents, they're added into that CT connection, and then the relay sees an overcurrent. If there is no circulating current, obviously, if there's just load flow, then they will subtract, because the currents will flow in the same direction for load flow towards the system, whereas in the circulate current, they will flow in opposite direction in and out of the winding, and they will add instead of subtract. The other split phase protection is using two CTs. So we need two CTs, one in each of the generator winding. And again, it's the same principle. If there's a circulating current within the winding, they add. Whereas if there is a load currents or external fault currents flowing, they will subtract. We also balance this by adding a positive sequence bias, or basically when there's load flowing, we bias against that load flowing through the generator, so be able to make the protection more secure and be able to protect for any of those phase faults within the windings. So we talk about the more common types of fault in generator or any type of protection system in general is the ground fault, right? And for a solidly grounded generator, not a problem. Ground fault current is pretty high. It's actually, for a solidly grounded generator, ground fault current can be greater than the three-phase fault current. So in that case, if you have a solidly grounded generator, and this can be mostly for sacrificial generators, low-cost generators where those generators are more sacrificial to the system because of that high level of fault current. If you do have a ground fault, the chances are you're going to permanently damage that generator and need to replace it. So this is always in the economics of scale here too. If you want to, protect a generator, you want to protect it properly from ground fault currents, you want to use a high Z grounded generator system. However, the protection system, the protection package becomes more costly because there are more different types of protection that you will need. Whereas with the solidly grounded generator protection, all you basically need is a ground overcurrent relay and you're protected. Whereas in the high impedance, there are lots of various different types of protection elements you'll need. We'll talk about them in the next couple of slides, but there are many methods for detecting the ground faults. So what you need to do is you need to know what type of grounding method you're going to be using, and you need to choose it wisely. Is it a generator is important to the process? Do I need to high impedance ground it, or can I solidly ground it and get away with just using a ground overcurrent relay? The 87G element is one way of protecting for ground faults. It can be set very sensitive, just like the phase fault current. It's the phase differential protection. It operates in the differential principle: current in equals current out, but it suffers the same situation as a ground over current element would. For faults close to the neutral of the transformer, you're going to have very, very low ground fault contribution, and your generator's ground differential might not be able to see that and might not be able to operate. So, so typical protection on low impedance, a solidly grounded system, you'll have a 51G ground fault, maybe even a 67N. We'll talk about why we might need a 67N in a slide or two, and maybe an 87 ground differential. If again, economics of scale here, obviously adding an 87 ground differential will require having another set of CT to be able to wire into that differential. If you don't have a second set of CT, then you might only be able to do a 51G. And again, these type of protection, they will be able to protect for majority of ground faults, except for faults right at the neutral of the transformer. And in that case, do you really need to detect for those faults? Because zero ground fault current, it's almost like having a solidly grounded generator anyway. So not a concern. The reason for having the directional ground over current element is if you have parallel generators, so fault in, for example, the system bus, both generator ground over current elements will see that fault and might trip both generators. So we won't be able to discriminate where that fault is. If a fault's on the left generator, same thing, the generator 51G will see that fault as well as the right side generator 51G, and again will unnecessarily trip its breaker for a fault outside of its zone of protection. So if you have a system like this where you have parallel generators, you might want to consider the 67N. What the 67N is, it's a directional element that looks at ground faults that are only flowing into that generator. So if there is a fault within the generator, that 67N on the generator will see that fault, whereas the 67N on the unfaulted generator will not see any ground fault because it only will see ground faults flowing outside of the generator and block from operating because it's only looking for faults into its generator protection zone. So the 67N senses revolves for a current and will not trip for an external fault, whereas for an internal fault, it will sense currents in the far direction and trip only its generator breaker. So help discriminate between faults between those two generators. So the 67N and 51N will detect the generator ground fault. The 51G will pick up for faults at either zone of protection, whereas the 67N will only pick up for faults within its zone of protection to provide that discrimination. The generator ground differential, again, same as the phase ground differential. It's discriminatory by default because it will only operate for faults within its zone, because within its differential zone, again, because the current in equals current out principle again. And it's so it's either you have the 67N or the 87N to discriminate when you have parallel generators running. The difference between the two is the 67N needs a voltage source to be able to polarize to tell what direction the fault's in, whereas the 87 needs two sets of CTs. So the balance is which one's easier to install, which one's easier or accessible to you. So coverage for low impedance ground faults or low or solidly grounded generators, the phase fault protection will not provide full coverage because of the sensitivity. So we need an element that will provide some sort of protection for faults close to the neutral of the transformer. Now, the phase differential will protect against ground faults, especially large ground faults that are, you know, maybe up to 10% of the winding of the generator, maybe up to 5%. But there is going to be about the 5 to 10% area where the fault's close to the neutral of the winding, where the phase fault of differential might not be able to discriminate between that fault and a fault at the neutral. So you might need a neutral differential or the 51G67N to be able to discriminate for faults close to the neutral of the transformer. Not transformer, sorry, generator. Oops. Now, what do we do when we talk about high impedance grounded machines? We mentioned is fault currents, ground fault currents are low or non-existent, very low or non-existent. So if we don't have ground fault current, how can we detect ground faults? Well, what other things do we have? Well, we have voltage. Does voltage give us an idea that there's a ground fault in the generator? It certainly does. So some of the voltage elements that we're going to talk about that is going to help us to determine ground faults within the generator zone is the 59N, which is an over voltage, zero sequence over voltage, neutral over voltage, all the same. This 57N is tuned to the fundamental frequency. So it's looking at whether it's 50 Hertz or 60 Hertz frequency of your power system. The 27TN is a third harmonic undervoltage element. We'll talk a little bit how that works. And that will also protect for faults, ground faults within the generator. And the 59D, which is similar to the 59N, except it's a differential. So it's a neutral voltage differential. And we'll talk about the advantages of using the 59D compared to the 59N. So to combine these three elements, we will get 100% fault coverage for the ground fault within the stator. So when we talk about ground faults within the generator for a high impedance grounded generator, the neutral grounded transformer is selected to provide a certain level of voltage, usually face-to-face, face-to-ground voltage at the machine terminals. So basically, we can look at the generator neutral and be able to determine if there is a fault, a ground fault. So normally in normal operation, when there is no ground fault, the 59N should see zero voltage. And as the ground fault occurs, depending on where in the winding, we're going to see high voltage. So if it's at the terminal of the machine, we'll see a full face-to-face voltage, 1 per unit. If it's close to the neutral of the machine, we'll see very low voltage. So for this type of protection, when it's at close to the neutral of the transformer, we won't be able to see that ground fault current. So that's why this provides about 90 to 95% coverage, because when the fault gets close to the neutral transformer, is basically close to zero, and we can't discriminate because of the sensitivity of the relay, sensitivity of the transformer that's reading the voltage, the inaccuracies in those equipment. We can't detect faults close to the neutral of the transformer, or about 0 to 5% in the low winding area. But it gives us a significant coverage, up to 90% most of the time coverage of the winding. Now, the 59N, usually we have two stages of 59. We have a fast 59N and a slow 59N. And why we have that is even though the delta Y transformer provides isolation, there is capacitive coupling across the windings of the transformer, which can allow a little bit of ground fault current to get across the winding. And hence, for system ground faults, we will see a little bit of neutral over voltage. So in that case, for low levels of neutral over voltage, we have a slow set neutral over voltage element, which is set to coordinate with our system protection or system ground protection. However, for faults within the generator, that face to neutral voltage, the 59N voltage, sorry, not face to neutral, but zero sequence voltage, will be very high, so we can set that close to instantaneously. So we usually have two stages: an instantaneous stage, which is set pretty high, and coordinated time delayed stage, which is set pretty close, low to coordinate for ground faults in the system. The 5027TN looks at third harmonic voltage, and why does it look at third harmonic voltage? Is the construction of the generator, the inaccuracies in the construction, the inaccuracies in the hookup of the generator causes third harmonic voltages to be generated while the generator is running. And we can make use of this phenomenon. The drawing in the graph A during normal operation, what we expect to see is a linear distribution of that third harmonic voltage from the neutral of the generator to the terminal of the generator, and maybe about 50% of the winding. If we look at that, at the voltage of 50% of the winding, obviously we can't, because we can't read that voltage. But if we did, it would be about 0 because of the linear distribution from the neutral to the terminal of the winding of the third harmonic voltage. So what happens is, if you have a fault at the neutral third harmonic voltage drops to 0, because now that neutral is basically grounded. So you move the neutral point of that third harmonic voltage. And similarly at the terminal, if you have a ground fault at the terminal, that linear distribution of the third harmonic voltage starts at the terminal now, where it's 0. So hence, that's why we can use the undervoltage 27 third harmonic undervoltage element to determine faults within the neutral or the terminal of the generator, because if the fault's at the neutral third harmonic voltage will drop. If the fault's at the terminal, close to the terminal third harmonic voltage will drop. So if the third harmonic goes away, we can conclude there's a ground fault, either depending where we're reading it, at the neutral or the terminal side of the transformer. Now, the problem with the third harmonic method is how to determine what level to set the pickups at, what undervoltage level to set at. It's very difficult to set it because we don't typically know what that third harmonic voltage is. We can empirically calculate it and determine it, but it's never gonna know for sure what it is until we run the generator. So it might be, we might need to run the generator, take some measurements, see what the harmonic voltage is. Not only that, that third harmonic voltage changes based on loading on the generator, based on the power factor of the generator. So the distribution of the third harmonic voltage changes as the operating condition of the generator changes. So that makes it very difficult for us to reliably set a 27TN element to be able to reliably detect for ground faults. However, the combination of the 59N and the 27TN allows us to get a good coverage. So the 27TN can protect for the last 15% of the winding, and the 59N will protect for the 90% of the winding. So they have overlapping coverage between the two. So normally we'll see a combination of these two types of protection. Due to the complications, as I mentioned, with determining the third harmonic voltage, for certain operating conditions, we need to block the 27 elements. So there might be certain operating condition, power factor operating condition, reactive operating condition, where the third harmonic voltage might be insignificant. And even though the generator doesn't have a fault, the third harmonic voltage could drop based on that condition. So we might need to add conditions where, depending on the operating condition of the generator, we need to block that 27TN. So during that time when it's operating in that condition, we will lose that 15% coverage in the remaining part of the winding that is not covered by the 59N. So also we need to block this protection when the generator is offline, because when it's offline, there's no third harmonic voltage being generated. So we don't want the element to trip. Obviously, it's not going to take the generator out, but it could prevent it from coming back online by locking the generator out. So the more reliable method that we have is the third harmonic voltage differential or difference. So what this method is, we're going to look at the terminal voltage, third harmonic, and the neutral third harmonic, and we're going to do a differential. So it's similar to the current differential, it's a voltage differential on the third harmonic voltage. So this allows us to be able to set the element without the concerns about the operating points of the generator that we talked about with the 27TN, because we're looking at voltage differential, we're not looking at an under voltage condition. So if we're in a part of the region where the term harmonic voltage is very low or non-existent, then we will not operate because the difference between the two terminal will be very low regardless. So the 2059D64TN element responds to third harmonic voltage measured at a general neutral and the general output terminals. When used in conjunction with the neutral overvoltage element, which is the fundamental element, the 59N, it provides 100% ground fault protection of the stator windings. The amount of third harmonic voltage that pairs in the neutral is both load and machine dependent, as I mentioned. Therefore, this method is more reliable where it's more adaptive to being able to not have to block this element during certain operating conditions of the machine. For a high impedance grounded machine, you should choose the neutral resistor such that the power dissipated resistor during a line to ground fault is approximately equal to the reactive power produced by the zero capacitance between the stator winding and the GSU winding. Again, as I mentioned, because of the coupling between those two, you want to be able to avoid issues for grounds that might be going through that coupling capacitance. So the advantages of, as I mentioned, of the 59D or 64TN over the 27TN, it can provide full coverage, and the security is not so much as a concern, but it can be less reliable than the 27TN. The third harmonic voltage magnitude is measured in the machine neutral via an auxiliary transformer. And then that 3V0 or the zero sequence voltage magnitude is measured from the terminal side of the transformer. So in that case, we either need a broken delta connection to be able to measure that 3V0, or we need a Y connected VT on the terminal side. Whereas in the 27TN, we only need to measure the neutral voltage to get the harmonic from the neutral voltage. So in conclusion, with all those various techniques for using to determine a ground fault current in a high Z impedance grounded generator is basically what we're looking for, a combination of these various methods that will give us good 100% coverage for ground faults on the stator winding. So it's usually a combination of the 59N and the 57TN, or the 59N and the 59D54S. The loss of field that I mentioned from the machine capability curve, the machine acts like an induction motor at that point. It starts to consume VARs from the power system, and it gets into the underexcited part of the machine limit curve. This could be due to a number of things. It could be the field breaker open, short circuit within the field, a loss of field supply. So basically, something's happening in the field where we've lost the ability to control the field, or completely lost the power supply to the field. It's bad for a system and it's bad for a machine. It's bad for a machine where the rotor now gets overheated because of the slip-induced currents, because the high currents in the stator gets induced in the rotor. The ability of the the stability of the system is now compromised because since the machine is sucking VARs, it's going to start to suppress the voltage. Then other machines are going to start to respond by supplying VARs, and they could get into an overexcited condition. So this could be a whole spiral stability where everything starts to spiral out of control, and we could have all the machines tripping and a widespread blackout. So we want to be able to detect for this condition, and we have the protection element we use is called a loss of field protection. It's a 40 NC40 number, and basically how it works is it has two Mohs circles, two offset Mohs circles. You remember our machine limit curve, the underexcited portion is usually in the fourth quadrant, hence why the Mohs curves are in covering the third and fourth quadrant there. And there's usually two circles, two offset Mohs circles for dealing with heavy load conditions and light load conditions. So in heavy load conditions, the offset Mohs is more stringent in that it will trip fairly quickly. And during light load conditions, we want to have some sort of delay because we want to not trip the machine for stable power swings where the locus or the electrical point will start to swing through this curve. And it's likely when it swings, it will swing through this outer region. So we want to be able to coordinate for our worst case power system swing conditions. Whereas in the inner circle, we call it, we want a limited delay, not instantaneously. And the only thing we really need to coordinate there with is maybe if we have a voltage fuse failure, voltage transformer detection, then we might want to be able to coordinate with that. So if there is a loss of blown fuse, a loss of an MCB, be able to detect that condition and block that element. So the power loss of prime mover. So what happens when we lose a prime mover? The motor, we have a motoring condition now. So we want to be able to prevent motoring conditions on the loss of the prime mover. Damage can be heavy depending on the type of machine. So so heavy steam turbines can have a lot of overheating in the turbine, can cause issues with the turbine, can cause explosions, can cause catastrophic damage. The reverse power element is used to prevent this condition. So the reverse power element basically looks at the motoring condition where the generator is seeing power go in the reverse direction. So we have a reverse power element that will detect that condition. And usually this reverse power element is set for sequential tripping, so that what happens is the power is backed off until we're importing a little bit of power so as not to trip when the system is exporting power and go into an overspeed condition. So if it's exporting power, we don't want to trip right away because that's considered a load rejection. We can go over an overexcited, overspin condition. So we want to back off the power a bit until we get slightly into a slightly importing power and be able to trip for that condition. And so we refer to sequential tripping. The generator accidental energization is one of the abnormal system conditions that we want to protect against. Since this is not a short circuit condition, backup relaying can only detect this condition. So primary relaying would not be able to detect this condition. We're talking about time over current, distance elements, unbalanced protection, reverse power with time delay on it. So it can cause time delays to pick up this condition. So they are usually slow and might be, and because the machine was out of service during this accidental energization, those pieces of protection might be out of service for maintenance purposes, for testing purposes, because usually when we take an outage, we're in a maintenance period where we're doing maintenance in our system. So the cause of the inadvertently energizing the machine is the operation error. Somebody inadvertently closed the breaker without the machine being ready to come online, control circuit malfunction, flash over the circuit breaker, even though the circuit breaker is open. Maybe there's some issues within the mechanism circuit breaker. Maybe there's moisture in the circuit breaker, and it can cause flashover, which will then cause power to then be going in the direction into the system, into the machine. So the machine is going to be drawing current. There's two types of energization: inadvertent energization, three-phase and the single phase. And in the case of the pole flashover or breaker flashover, it's usually a single pole flashing over, so it'll be a single phase condition. And what happens during this condition, again, because the induced currents within the rotor starts to heat up rapidly. And we're talking about, depending on the system that it's connected to, we're talking about you can have a very, very high draw, up to 3 to 4 times the rated current of the machine, which will cause damage to the machine if not detected. And the way we detect this is fairly novel method of detecting energization. So we know when we de-energize the system, so either the breakers open up or we have an under voltage condition. So once we go into take the generator out of service, we enable the inadvertent energization protection. So if we have the breakers open or we have a de-energization of the generator. And then when we energize the generator, we want to wait for a period of time to see if we see elevated currents. Remember, we talked about they could be up to 3 or 4 times rated. So we have a 50 element that will be enabled for a short period of time after we energize the machine or inadvertently energize the machine. And if we sense high currents during that period, we will trip the generator. So this protection is only armed when the generator goes offline, and it will only trip for a period of time that it's user settable. It could be a couple of cycles to however long the machine usually stabilizes in. So it will depend on certain system conditions. So you set those delays within the protection system to arm and then trip within a time period. So when we talk about unbalance, what kind of conditions will cause unbalance in the generator, or what kind of conditions will the generator see unbalance in? Obviously fault currents, but there are other scenarios where we'll see unbalance. Open phases, dumb conductors in the system, if it's an overhead line, untransposed transmission lines where we have coupling across the transmission line, the various phases of the transmission will couple against each other, which will cause unbalance within the system. Unbalanced loads, obviously, and those unbalanced conditions produce negative sequence currents. The negative sequence currents rotate opposite the positive sequence, and they generate a 2 times current in the rotor. So 100, say if it's a 60 hertz, it generates about 120 hertz current in the rotor. And that current will cause skin effects, and the current will flow into the rotor bar, cross-sectional area where it's not meant to be, and again, heating in the rotor can occur, and over time, damage to the rotor. The rotor bar impedance increases and eventually damaged. So how do we protect against this? Fairly simple. We have a negative sequence or an unbalanced relay, which is looking at the 3 phase voltages and seeing what kind of unbalance we have across the 3 phases. And then we will trip appropriately depending on the amount of imbalance. And this again might be coordinated for external fault conditions, because again, if the system is solidly connected, it's not going through a GSU, a ground fault out in your system will cause an unbalance. So you want to coordinate with those situations. The power system block is the basically when a stable power system can be seen as a condition when the system loses synchronization for a period of time with the neighboring system, and then later regain synchronization. There are two reasons which can cause this type of power swing, and those are one which uses a significant amount of generation, instantly becomes much weaker, but the load of the system remains constant. And then the other is if the system is already weak and the load suddenly increases substantially. So the power will start to swing. So if that power swing, or what we call the electrical center of that power swing, swings into our GSU or a generator, that can cause the generator protection to either see that as a fault, or if it's an unstable power swing, we need to trip that generator. So we might need to block, or we might need to trip. For a stable power swing, we need to block protection that might be, we might need to block protection that can be susceptible to misoperation for that power swing. And if it's an unstable power swing, we need to be able to trip the machine to prevent damage to the machine. So when a machine goes out of step with the system, it accelerates or decelerates depending on the type of power swing. It starts to sip poles, again, resulting in damaging vibration issues, heating issues. And this is of concern when the power swing locus, the electrical center, passes through the GSU or generator. The generator can accelerate or decelerate, changing the voltage angle between itself and leading to an out of sync condition. These high levels of transient shaft torque are developed and can break the shaft over time. High stator core end flux can overheat and short the core. The GSU itself, the transformer, can be subject to high transient currents, such high overheating of the transformer. How do we detect these power swing conditions? Is we have a Mohs circle, an impedance circle with a left blinder and a right blinder. The two blue lines is the left blinder and the right blinder, and then the dotted line is our Mohs circle. So when we have a stable power swing, the locus will come into our Mohs circle and maybe into our right blinder, but then it will exit back to get to a stable condition. But most of this, when it's an unstable condition, it will swing from the load point on the right through the Mohs circle, through the right blinder, through the left blinder, and out the Mohs circle. So we can tell the difference between a stable power swing and an unstable power swing by looking at that locus and the time that that locus moves through the Mohs circle and those two blinder settings. Our strategies for tripping are during blinder exit or Mohs exit. So when we talk about blinder exit, we're going to trip when the unstable swing exits the left blinder, the blinder that's in the negative region. The issue with that can be because we're still very close to the power swing is still very close to the generator at that point, we can see high currents, and that can cause stress on the breakers, where if we call upon the breaker to open, it can stress the breaker. So if we want to not have too much stress on the breaker, we can wait until the power swing gets to the exit of the Mohs circle. In that case, where the currents, now the power swing is further away from the generator, and the currents are lower, and we have less stress on the breaker. The generator over or under fluxing conditions can be caused, overfluxing conditions or overexcitation conditions can be caused where the AVR, the automatic voltage control, have a problem. There's a blown fuse. The machine is down, is speeding down, so the frequency is reducing, and we have basically an excitation above the limit of the machine. In terms of voltage, the light loading causes the system voltage to rise and frequency to decrease. Incorrectly switched caps and reactors can cause this. Excitation boost from loss of nearby generation, low frequency at these elevated voltages. So we can't just look at a voltage and frequency by itself to determine this condition. We need to look at both, and that's what we refer to as our volts per hertz protection or overexcitation protection. So we look at the ratio of voltage to hertz. So if that ratio is fairly high, we have high voltage, low frequency, then we know we have an overexcitation, overfluxing, and we can trip. And this does not only apply to generator, but any type of power system equipment that has a magnetic core, including our transformers, where the flux density will oversaturate the transformer core and cause it to go into a condition where the volts per hertz will be elevated. The generator protection guidelines that we can use to refer to when we determine what type of generator protection, and a lot of things that I've talked about come from these guidelines. There's some things that I didn't talk about, like injection for stator ground faults, and some other techniques that we use were for not applicable so much industrial, but more utility side. So we're talking more on the industrial side. We didn't talk about some of those techniques, but you can look at these guides to see some additional techniques, including the subharmonic injection to determine ground fault currents, ground faults within generator, high impedance grounded generators. Let's take a look at an example of the IEEE 242 IAS book, and basically this is again referring to mostly industrial generators, small to medium generators, where it's usually maybe not have a differential or not have some. It's usually an impedance ground, a low impedance grounded or high or solidly grounded generator, so fairly straightforward. We can have overcurrent elements. The 51V element is a voltage restraint overcurrent element. So it might be cases here if I have a high impedance to ground fault somewhere, then I can look at current and voltage because my current is going to be low. I want to look at voltage also to see that the voltage is depressed, to be able to tell that there's a fault on that generator. And then when we talk about the medium volt, we go up from small to medium voltage generators. The additional protection could be an 87. Again, the 87 will require additional CTs, require additional relays, a little more testing involved to commission and such. Then when we talk about going to higher large generators, this is what most of what we've discussed today. We talked about the 59. And we talked about the 87 phase, the 87G, the 64 third harmonic differential, the third harmonic undervoltage, the zero sequence overvoltage. So all of those are covered within these guides. So if you want to, and then when we talk about really, important generators to our system, then we're talking about something like this in the C37.102 guide, where, as you can see, there's a lot of protection elements. A lot of them we've talked about, the 87. There might be distance, the 51V, to be able to back up for system faults. So coordinate for system faults, auto-zone faults, or inadvertent energization, the loss of sync or auto step, or 78, loss of field protection, reverse power for loss of prime mover, our volts per hertz because for overfluxing, and our 59G and our 27 TN or 27 under voltage or third harmonic voltage differential. Some of them we didn't talk about, like the field ground and the ground injection, because they're more, as I mentioned, for larger generators, not so much see them in the industrial sector. So with that, we've come to the conclusion of the part of the presentation where we looked at the various protection techniques that we use for generator protection. And we will look at the 889 relay a little bit, and how do we set that up for the various type of protections that we talked about. So when we come into the EnerVista setup software, there's two windows that we first see when we enter the NVISTA software window. The top window, which we call the online window, and the bottom window, which we call the offline window. The online window is when we're connected directly with the relay. So everything we do in the online window is live on the relay. So right now I have a relay on my bench here connected. So I'm going to go into that relay. Unfortunately, I don't have an 889 relay on my bench. So this is an 869, which is a motor relay. But all the 8 series follow the same convention. Whether it's an 889, 869, all the menu structures are all the same. The only difference is the type of protection that they have. Obviously, the motor protection has a terminal overload model, and the generator protection has all of the various protection schemes that we've just talked about. So when we come into the online window, there's a couple of things that are important to note. So first of all, before we talk about those elements, is how do I connect to the relay? There's a couple of ways to connect to the relay. One is the quick connect, and obviously, as the name suggests, is the quickest way to connect to the relay. So if I click on the quick connect, there's a number of ways to connect to the 8 series. There is the USB front port, which all you need is a device USB cable. It's exactly the same cable as your printer cable, so you can get this Amazon, Best Buy, wherever it's a commonly available cable. You can connect through Ethernet. The 8 series can have up from 1 to 2 Ethernet port, but 2 Ethernet port comes with the advanced communication model. So right now I'm connected through the Ethernet port. With the Ethernet port, you need to enter an IP address. There's also an option to have Wi-Fi. So if you do order a relay with Wi-Fi, you can connect via Wi-Fi. But note, you do need a hotspot for that. You need a hotspot for that relay to connect to, and then you connect to the hotspot to connect to the relay. So when we connect to the relay, this is on the left top. This is the menu that we're going to see. And you'll notice there are a bunch of icons on the top. The first icon to the left is what we refer to as the sequence of events. Icon. And there's something is up on my relay. It's not communicating at the moment. Might be because I'm on the corporate network at the moment. So unfortunately, I won't. It knocks me out when I try to connect to the corporate network off of my local Ethernet connection. So anyway, so the sequence of events connection is icon is to look at the sequence of events in the relay and to see what is going on in the relay in real time. And usually if there's a trip, there's certain control functions going on in the relay. They will all be timestamped, show up in the sequence of events. The next one over is the oscillography. The oscillography is basically a COMTRADE, so that's a snapshot of the power system that was captured during some sort of disturbance, whether it's a trip. But you, as a user, have to set up this oscillography trigger. And it's very important, so I want to show you that. It's very important to set up that oscillography trigger so that it captures what you need it to capture. So by default, it will capture all the currents and voltages that are available in the relay. So if this is an 889 with a differential protection in it, then there's 2 sets of CTs, maybe a VT and maybe an auxiliary VT. You want it to set up to, obviously, the trigger source. You want to set it up to trip, so any trip to be able to generate that oscillography. And additionally, maybe there's other elements. Maybe you also wanted to set up on pickup. Pickup is basically if you have like a time over current element, you have a fault, the time over current element picks up, it hasn't timed out yet, it's waiting to be timed out. So you can have a record created when it picks up and a record created when it tripped, because the time between pickup and time between trip could be a long time depending on your TOC time dial setting. Then the other things are digital inputs. So what do you want to see in the oscillography so that you can align what's going on the power system to what's going on in the relay. And then you have some analog values that you can set. So these are like filtered data, filtered measurements in the relay or calculated measurements in the relay. And these can be various different elements, and we have up to 16 of these analog elements that you can program. In my case here, if this is a differential relay, I want to look at the differential currents and restraint currents that the relay is calculating, or I want to look at the third harmonic voltage that the relay is measuring, right? Because we want to see, if we're doing a third harmonic voltage element, we want to see what the voltage difference is. We might see the unbalanced currents that the relay is calculating, and so on and so forth. So whatever you as the user want to see in the oscillography, you should come in here and program that appropriately, so that when you do have an event and there may be a problem, or not even a problem, the relay might have operated correctly, but you still want to analyze that event to see, hey, did the relay react to what I expected it to, and did it react to part of the power system conditions? Because a relay could trip, but it could trip, we call that a trip but unexpected. So it could trip, correct trip, but undesirable. So it's a correct trip, but it's undesirable in that it actually didn't trip because of the way I set it up. It tripped for a different reason. So even for a correct operation, you might want to take a look at what's going on with the relay, because it might, in a future incident, it might be the opposite, where it might not trip for what you want it to. Now, one icon I want to mention, this icon on the top right here, it's called the service report. So the service report is very important in terms of, if you want us to look at something that's happening in your power system, something that's happening in your relay, you have a disturbance, and the relay might have tripped, and you didn't expect it to trip, or it did trip, but not what you expected to trip on. So what we would normally ask you to do is send us the service report. So just clicking on this icon, the relay will download the service report. And that service report contains every element in the relay. So it contains a setting file, it contains the oscillography, it contains a sequence of event, it contains any data that's logged in the relay, it contains any diagnostic information that the relay is gathering, it contains RTD readings, it contains metering information, it contains a whole host of stuff. With just one click, we can gather all of that, and it zips it into one file, and then you can forward that file to anybody, and that person can unzip that file and look at everything that's available in the relay. So it's very easy method to grab everything from the relay, but just be aware, it might take some time depending on how much oscillography, how much sequence events available in the relay, because it's a lot of data to capture. So be a bit patient with it when you do it. So let's go into the offline window. And the offline window is basically where, as maybe a protection engineer, where you would create settings, or you would look at the settings that was downloaded from a relay, or as I said, create settings. And the way you would create a setting is you would go to right click on any of the three items and click on new setting file, and basically you just create a model number based on the relay that you've purchased or the relay that you've installed, and you just match up the model number to that relay. And every option is available for you to select, so you know exactly what those models mean, what those numbers mean in the model number. The other thing is you want to add an existing setting file. So somebody emails you a setting file, you save it on your desktop, and you want to view that setting file. So you click on add existing setting file, and then you browse to the location where you've saved that setting file, maybe in your desktop. And then you open that setting file, and then it will appear in your offline window. In this case, I have an 889 created here. In the 889, I'm going to go to the quick setup. This is a way of quickly setting up the entire relay in one or two screens. Instead of trying to navigate all of the various screens, I can go to this quick setup screen, and in two windows, I can set up all my protection elements that I need. So in this screen is obviously you're going to set up all your CT and PT ratios, your rating, generator rating. If this was a transformer, if you had an in-zone transformer, your transformer rating, and your CT, PT ratios. If you have multiple CTs, which you would for differential protection, then you would add, and they're varying CT ratios, then you would adjust them accordingly. And then you will select, the relay 1 by default in the H series is the tripping relay. So that's why we usually name it the tripping relay. And I recommend you keep that the way it is. So don't change the functionality of that relay 1 or relay 2. Leave those as default, which is the trip and close relay. And I'll explain why when we go to the protection element setup that is. So then the second screen is where we actually set our protection elements. And you can see my differential, my percent differential, my phase differential protection. I set up here with my slope settings, my pickup settings, as we mentioned when we talked about it. And this function that I've selected here is the trip function. When I select the trip function, that is automatically mapped to the trip output contact. So I don't have to do any logic mapping. Once I've selected trip, the relay knows automatically that I'm going to hit auxiliary relay 1, which is the trip relay. So by leaving it at the default trip relay, it makes everything easier for you to, once you select trip, it will automatically hit that trip relay. And the loss of excitation, all the settings available with the loss of excitation, I mentioned the 2 offset circles, circle 1, circle 2, and then the 2 time delays associated with those 2 offset circles. So as you can see in this case, my case, I have one set up, the shorter or the inner circle set up with a shorter time delay, and the outer circle set up with a longer time delay. I don't have the inadvertent energization enabled, so that's why it's disabled. To enable it, all I have to do is hit trip and hit save and basically enable the inadvertent energization. And these are my basic settings for the inadvertent energization. The overcurrent, remember that 50 element, the pickup of that, and then the undervoltage element. And then the arming mode, where the undervoltage and offline. Offline is basically if we're monitoring the generator breaker, when the breaker opens up, that's basically the generator going to offline. So we can monitor the voltage and the breaker, and either one of those we can go into this protection, or if both. I should expect to see both when the generator is offline. I should expect to see the breaker open and the voltage bus de-energized, the generator bus de-energized. Then we have, I also have the generator unbalanced protection enabled. This is again percent of full load rating. And there's some time settings. So in this time, this is very long. So there's something I'm coordinating with that has a very, very long time delay that's out of my system. And then my various other elements. So these are the most common and basic elements that we would use for an industrial generator protection. Some of the elements that we talked about that you don't see in here is like sorry, not the directional power element. The directional power element is here, is the out of step condition. So the out of step condition is not available because it's not commonly enabled or seen in industrial applications, mostly on utility type applications. So once I've done that and I save that, I basically set up my relay to trip for those elements, and I'm basically done as long as I've set up my oscillography properly. Now, if you're looking at an existing setting file and you want to see what's in that setting file, what protection elements are enabled, an easy way to get to that is from the protection summary, right below the quick setup. And the protection summary will show me all of the available elements in the relay, all the protection as well as monitoring and control elements. If I'm setting up the relay, then I can click on these elements and set them up. Or if I'm looking at the setting and I just want to see what's enabled, I click on the enabled. and will only show me the elements that are enabled. In this case, the phase differential, as we saw previously from the quick setup screen. I click on it, and it will take me to the settings of the differential protection. Same thing if I go to the loss of excitation, it will take me to the settings of the loss of excitation, the 40 element. And again, it's set to trip, it's set to trip.output contact. And then there's a circle 1, circle 2. Important in the events and targets here, you want to enable the events and targets. You want to enable the events when you enable an element to trip because you want it to show up in the sequence of events. If you don't enable it, it will not show up in the sequence of events. Depending on the type of element that you're enabling, so if it's a tripping element, I usually recommend setting the targets to latch for any tripping element because you want to see what element tripped the relay. Because if you set it to self-reset, if the breaker opens up and say it's an overcurrent condition and that overcurrent goes away, then those elements will reset. You go in front of the relay, you will not know what caused that trip because those elements have reset. And then you would have to go into the sequence of events and look in the time stamps to see when that relay tripped and when and what elements tripped during that time. Whereas if you have a latch condition, when you go in front of the relay or you access the relay remotely following an event, you'll see all of the latched elements that are up on the relay to tell what has caused the trip. And when you press the reset button, whether locally or remotely on the relay, then it will unlatch those latch conditions. That's the only element I mentioned that's not part of the quick setup screen was the out of step condition. And I just wanted to show you the out of step condition what we talked about. Again, I need to enable it to trip. Well, if there's an element like the out of step condition, maybe I don't want it to trip. Maybe I want to enable it to either block something or only alarm for me to know that I have an out of step condition and I might want to look at something. So I don't have to necessarily trip. I can go to alarm and this will hit the alarm LED, or I can go to configurable. And when in the configurable setting, what I do then is I can select which relays, which output contacts I wanted to energize. So if I didn't want to hit the trip contact, I want to hit another contact, then I can go and I can set it to configurable. It will not hit the trip contact. And I just check the contact or contacts that I want it to hit. Now, if this element operates, it will go and it will hit relay 10 and 11, but it will not trip. It will not hit the trip contact. And again, we talked about the blinder settings, the left blinder, right blinder setting, the MO settings, the forward and MO settings to set that MO circle for the out of step condition. The trip mode we talked about, if it's the MO exit or the blinder exit, depending on the stresses that the breaker is going to see, that will depend on this setting, and then time delay and the various pickups. The only other thing I wanted to mention is when we look at the power sensing, you'll know when we set up the power where you'll know there's a settings that says CT and VT polarity. Remember I talked about that differential? So depending how you set up that differential connection to do the differential, whether it's just whether it's just a generator zone or whether it's a transformer in the differential zone, the connections might vary a little bit. So you might have to come in here, and if I want to meter correctly, meaning I want to save power leaving the generator or going into my system, then I may need to come and reverse the connections here so that my forward metering is correct. And with that, we have about 15 minutes that we can answer some questions. I think most of the questions seems to be answered. I don't see any new questions coming in. So one of the questions I get a lot is when we talk about generator protection is for high impedance grounded generator, we talk about the coverage for ground faults up to 100% of the winding, right? I talked about it for low impedance and high impedance. Why does in low impedance it doesn't matter much, right? If the fault is on the if it's solidly or low impedance grounded, the fault's close to the neutral. You don't see neutral current, so not a problem there. Is it a problem on the high impedance grounded? So say I have a fault at the neutral point, ground fault at neutral point. Do I really need to detect that fault? Yes, I do. And it's very important that I detect that fault because what has just happened? By having a ground on the neutral, what I've done, I've bypassed my high impedance ground, right? Because now I've connected the neutral to the ground. So I bypassed that high impedance ground. So my generator is not a high impedance grounded system anymore. It's a solidly grounded system. So if I have another ground fault within my generator, that can cause lots of fault current to flow into my generator, maybe even more than my three-phase fault current, and cause a lot of damage. So I need to detect faults all the way to the neutral of all the way to the neutral of the generator winding to detect any type of ground fault, because that's just an accident waiting to happen if I neglect not to detect the fault on the neutral, a grounded fault on the neutral. Terry or Christine, is there any questions that you guys that you've answered in the chat that you might want to answer in the main? No, okay. So we have about 15 minutes. What we can, I did have a couple of backup slides. So what we could do in those 15 minutes, unless again you guys have questions, please type it into the Q&A and we can answer them. Terry and Christine has answered most of them in the chat already. So let's talk briefly about how do we. Go ahead. Sorry.
I think Terry was going to speak there. Go ahead.
Go ahead, Terry. Sorry.
I might have unmuted my mic, but I didn't have anything to say. Sorry.
Okay.
Okay.
No problem.
Go ahead.
Okay. So let's just talk briefly about setting the differential, because that's a pretty important element when we're talking about differential protection to set. And this doesn't just cover generators, but it applies to transformers, buses, and any type of equipment. And one of the things we talked about is we don't want the Achilles heel of a differential protection is saturation, because that causes differential to flow in the circuit and could cause misoperation. There's ways we could deal with it, and we've talked about. So, what are we talking about when we talk about how do we select the CT to prevent saturation? One of the good tools is the IEEE tool, working group tool, that it's all available on our website. It's not a tool owned by GE. It's available on our website if you want to download it. And it's a very, very good tool where you can enter your system parameters, your X over R ratio, your CT class. So it's a C400, C800, your winding resistance of the CT, your burden resistance of the wires, your CT wires, or the burden resistance of your equipment. Again, you could see this one here where I have the burden resistance is at 0.004 ohms, which is very, very insignificant compared to the burden resistance of the CT or the winding resistance of the CT and of the cables. And that's because this is probably a microprocessor relay and it has very, very insignificant burden compared to the other factors. Then we put our maximum short circuit current, and then the tool gives us how the CT will perform during that condition. In this case, there is saturation, but saturation doesn't occur until about 4 cycles into the fault. And that's okay because we expect our differential to operate between a cycle, less than a cycle, maximum 2 cycles. So that's not a problem. So the CT is sized properly. So this is about a C400. So this is sized properly for that condition for 50,000 amps of fault current for an high X over R ratio of 20, and for maximum offset or DC offset. So now I know that CT is okay. How do I determine, how do I set the breakpoint? The second breakpoint is where slope 2 begins. And remember, that should be set where for an external close-in fault where my CTs are going to see maximum amount of fault current. So I want to set that with some sort of margin within my maximum fault current. In this case, I dropped it to maybe 40. Remember, it was 50,000 amps. I dropped it to 40. And I might even want to go lower because even 40 might be a bit high. So I go about 4 times CT, which is 32. So some margin from your maximum short circuit current that you want to set it at. This could be 70 to 80% margin. Again, this depends on experience, depend on the person who's doing the settings, and so on. So, and then what about the slope setting itself? The slope setting is applicable for the restraint current, again, above breakpoint 2. This slope is set to ensure stability under heavy external fault condition that can lead to high differential currents as a result of CT saturation. So remember, the relay looks at differential over restraint. So the higher the slope, the more differential current the relay could deal with without tripping. So, and that's what happens during a saturation condition, is we see more differential than restraint. So if you have a condition where it's where you're going to see high saturation, then you want to set the slope pretty high. And we usually recommend 80 to 100%. That's some of the default settings, I think, is close to that. And this is based on a lot of studies we've done for a lot of different fault conditions versus system conditions. So this is a very, very good compromise. If you don't have the ability to get all that information and do all of the calculation to determine exactly if your CT is saturating, how much is it saturating, and do the calculation. The slope 1 is applicable for regions after breakpoint 1, so between breakpoint 1 and 2 and above the pickup. So it defines the ratio of differential restraint above where the element operates. The slope is set to ensure sensitivity for internal faults at the nominal operating current levels. So this might be set to conditions such as CT inaccuracy, CT matching, relay inaccuracy, equipment inaccuracy, or issues caused by maybe DC offsets, because DC offset, any CT I could saturate at any point with DC offset. So if you have a case where you will see high DC offset, you might want to adjust the slope. Good value is 10%, and again, based on system studies, based on conditions we've seen in the field, 10%, about 10% is a good compromise. If you have DC offset that can cause your CT to go into some level of CT saturation, then maybe 30%, 40%, even 50%. Some people actually can set slope 1 and slope 2 the same setting because their CT selection is god awful, and it's a really bad performing CT, and they might need to set the 2 slopes the same. So then the transition between when you go from slope 1, where you start the spleen, to go to slope 2, should be set above the maximum operating current, or like your full load current. So good margin is about 1.5 times your full load current. And if you've sized your CT properly per your full load current, it should be about 1.5 times your CT rating. And then your pickup setting should be set such that it will handle any type of standing differential that the relay will be calculating normally when it's a normal operation. And why would you calculate standing differential during normal operation? A couple of things. One, CT inaccuracy. At worst, relay class CTs are only required to be 10% accurate. That's a lot of inaccuracies there. You can get CTs that are better than that, obviously, but the standards at minimum requires a 10% accuracy for relay class CTs. Then the other conditions, for example, might be like if you have a transformer, if you're protecting differential of a transformer, you might have different winding taps, which can cause inaccuracy. So you want to set the minimum pickup a margin above any type of inaccuracies that will cause standing differential current to be seen by the relay. I know sometimes you might not be able to calculate these or not know these, correctly. So sometimes what I do, I set it maybe 0.3, 0.4 per unit. I put the relay in service, and then I monitor the relay, and maybe I'll sensitize it a little bit more depending on the differential current that I read during normal operation of the relay.
Hey, hey,
Go
Mike.
ahead, Terry.
A good question just came in. I thought I'd interrupt you and let you answer it rather than type it out myself. So the question was, why are we not using 50 instantaneous overcurrent protection in high capacity generators?
So a couple of things with that. Usually, as I mentioned, for example, let's talk about phase faults. So we don't want to set a 50 instantaneous overcurrent because for faults out in our system, that 50 instantaneous will see those conditions. So we might erroneously overtrip the generator for faults outside of the system. So we want to coordinate for the faults outside of the system. Now, when we're talking about large capacity generators for ground faults, they're usually high impedance grounded. So with a high impedance grounded system, you can't set an overcurrent element as we've talked about. So there are some limitations there. And Terry, any other thing I missed?
The one thing that I always think about for a fault on the generator terminals is that when you initially strike that fault, even if it's a phase-to-phase or even a three-phase fault, you will produce a lot of you'll produce a lot of fault current for a very short time. And so, that's given by the subtransient reactance of the machine. But after a very short time, the voltage will collapse to the point that the current that you're providing to that fault is typically less than full load amps of the generator. So for that reason, you can't really use even a time overcurrent or an instantaneous overcurrent because they likely wouldn't pick up, or if they did pick up, they'd drop out before they had time to expire in the case of a 51. So the way that you really need to do that sort of backup protection is with something that uses voltage as a restraining quantity.
Right.
So you either use a voltage restrained 51 element or a phase distance element.
Correct. Right. And then that's what we've seen in that slide on the C37 102. As Terry mentioned, we didn't talk much about the 51 or the 21 because it's mostly for backup protection. And it's at the bottom here, 21. So it's a substitute. Either one will work depending whether you use the 51V or the 21 will depend on the impedance that you have to read. So if the impedance is really small, you might not be able to set the distance, and then you might just need the only option is to set a 51V. And with the 51V, it's basically, as Terry mentioned, it's looking at voltage collapse as well as current. So in that case, you might have a low current, but since the voltage has collapsed to a point, you can still operate with that element. Whereas for loading conditions, when your current, for high loading conditions, your current can be above the pickup of the 51V, because you're in a normal condition, your voltage is not below, for like in the case of a phase to ground fault, so you will be restrained from tripping. And with that, we've kind of come to the conclusion of the seminar. I hope everybody got what they wanted out of it. If you have any questions, please feel free to reach out to us beyond this call. And reminder again, send your name. If you've attended it, please put your name in there so we know who's attended. And if you've called in and you don't have your name in there, it's very difficult for us to determine who's attended it, because when you call in, it just shows an anonymous, or if you've logged in as anonymous. And the recording is available for at least 60 days on the same link that you used to join. So if you go to that link, the recording will be able, and you can fast forward, rewind it to get to a point where you just wanted to hear Terry's voice, you were tired of hearing my voice at the 58 minutes or whatever it was, 350 something, whenever Terry came on. So thank you, everybody. Have a great day.
Just want to mention, we will thank you everybody for joining. We'll be having another webinar, similar structure, on the topic of transformers in 2 weeks. We'll be sending out the invites shortly to that, and we thank you very much for your participation, and thank you, Mike, as well. Have a great day.
Thanks.